Greetings and welcome to another installment of QuantSlob. This is 40 in our basic application series, and this time around we're going to kick off Season 5 with Part 1 of an exciting 18-part series covering simple linear regression. And yes, you heard correctly, 18 parts. When I started putting this simple linear regression series together, I was thinking maybe like 7 episodes, but it just kept growing and growing and growing. So I guess the big takeaway is that simple linear regression ain't so simple after all. But anyway, so before taping a series, I like to have all the episodes mostly complete to help assure that the notation and terminology are consistent. And this in part explains our long intermission producing videos. It's been, in fact, a little bit over a year since we concluded Season 4. And I also wanted to mention that during this time, we received a number of donations to QuantSlob. This is extremely cool. So thank you very much for staying faithful and being patient and contributing if you are able and interested. Okay, simple linear regression, or SLR for short. It is a special case of the larger class of regression methods, and pretty much everyone has heard of regression, I think. Regression is very popular, powerful, and useful within science, and with its power and utility comes a massive, massive constellation of methods, calculations, diagnostics, and of course, in turn, a massive specialized vocabulary. Terms like best fit line, influencer. You like the Star Wars style crawl text here? Anyway, to simplify things, the upcoming 2 installments, including this one, we're going to focus on calculating our regression line along with some interpretation. But importantly, we're going to be working in a descriptive setting. That is, we're going to treat our data set as our target population. Then after an installment offering a very brief history of regression, the remaining installments in this series will focus on SLR in an inferential setting. I think limiting ourselves at the outset to a purely descriptive setting removes considerable complexity. It's just a nice icebreaker into the larger topic of linear regression. Descriptive statistics treats our data set as our population, and our goal is to describe what's going on within our data set. That is our population. If our data set is a subset of a larger population, or we're assuming it is, then we may use our data summaries to make inference to patterns within the unobserved target population. But before jumping in, let's take a look at a Season 4 legacy, our QuantSlob challenge from Part 11 of our Summarizing Data series, if you remember that far back. So anyway, looking at these 2 word clouds, what differences really stand out in terms of the lyrical vocabulary between our top 5 Opeth songs and our top 5 Taylor Swift songs? Now remember, the key theme we introduced way back in Part 1 of Summarizing Data? Data summaries are really about facilitating comparison. And these word clouds certainly supply rich fodder for comparison, so the things that stand out to one person may not be the same as those for another, but I'll share what stands out for me. Okay, with Opeth, notice the popularity of prepositions here. In, with, to, here, outlined. Compare this with the stark relative infrequency with Taylor Swift. In fact, I would say these 3 words are kind of even hard to find in the Taylor Swift word cloud. I want to mention that computer software for text analysis often treats prepositions as so-called stop words. It will remove them from text. I have never been a fan of this, as prepositions can really tell a story about a document, like here, for example. Now, conversely, notice the popularity of personal pronouns in our top 5 Taylor Swift song lyrics. Personal pronouns, you, I, me. Here. These do appear in Opeth lyrics, but they are much less relatively prominent, meaning that they are much less relatively frequent. Okay, moving on. As mentioned a moment ago, SLR, simple linear regression, applications form a proper subset of the larger class of regression methods. They represent regression methods that are both simple and, well, linear. Linear, that shouldn't surprise anybody. We'll explain what we mean by simple and linear here in just a moment. To offer a more holistic view, we can think of regression methods as overlapping with the larger art of supervised statistical learning. The term statistical learning is pretty much synonymous with the more familiar machine learning. You probably heard of machine learning. Statistical learning is absolutely concerned with inference, oftentimes forecasting, that is, forecasting ahead in time. like forecasting the future value of a financial instrument, like a stock, or say forecasting the noontime temperature in downtown Dallas tomorrow. Okay, it also includes lots of other things. It includes tools for model selection, like answering the question, is simple linear regression even an appropriate way to describe the relationship in our data set between two variables? Supervised statistical learning is all about statistical inference. So we could think of our little crescent here as representing simple linear regression in a descriptive setting. The blue outlined region here that overlaps with the big supervised statistical learning circle represents SLR applications that are inferential. Okay, SLR, simple linear regression. Simple, a way of characterizing the relationship between two numerical attributes. Simple as opposed to, say, 10,000 numerical attributes, which would not be so simple. Conventional notation calls the two attributes x and y, or more particularly, we can call x our independent variable and y our dependent variable, or we can call x our input and y our output, or more generically, we can call x our predictor or explanatory variable and y our outcome or response. Simple linear regression, linear as in line, linear, line. Okay, often in textbooks, the line function is notated using b, the letter b, for the y-intercept and m for the slope. However, these are just placeholders, and as we shall see, we can and do notate them in accordance with whatever convention is appropriate for our application. And math is really about a lot of bookkeeping, keeping track of our notation. Okay, line function. Let's look at a couple examples. So here we have a Cartesian space, Cartesian representation. Here the x-axis and y-axis take on their mathematical meaning. That is, they intersect at the origin 0, 0. And speaking of bookkeeping, check out our line function. We here are calling our y-intercept lowercase beta sub 0. We're calling our slope beta sub 1, and the value returned by our function is represented by a y with a little hat over it. Little hat, y hat. Why are we notating our line function this way? Well, to get us ready for what's coming next in this series. It just happens to be conventional simple linear regression notation, specifically when describing a trend between x and y within a population, descriptive stats. Okay, so for the sake of example, let's say our y-intercept is 0 and our slope is 1. Notice we've added scale to our graph. So the width of a major grid on our graph paper has 1 unit x and height has 1 unit y. When x equals 2, y hat equals 0 plus 1 times 2, y hat equals 2. When x equals negative 2, y hat equals 0 plus 1 times negative 2. So y hat equals negative 2. And of course, on a plane, two unique points define a line. So presto. Notice the value of y hat at the point where the line crosses the y-axis is 0. The value of the y-intercept, that is certainly not a coincidence. The line slope is sometimes called rise over run. Increase in y, rise for a 1 unit increase in x, run. When x increases by 1 unit here, our line value of y hat increases by 1 unit. 1 over 1 is 1. That's our slope. One more example. Here, our line function is negative 1 minus 2 times x. Our y-intercept, of course, is negative 1 here. Rise over run. If x increases by 1 unit, y hat increases by negative 2 units, or in more familiar terms, y hat decreases by 2 units. So there we go. Isn't that nice? Looks pretty good. And just like that, that's it. That's going to do it this time around. Thank you so very much for tuning in. I really do appreciate it. Don't forget to stay tuned for more Quant Slob.